Okay, welcome to the Classics in Immunology Journal Club. Today we're in the 1960s, 50 years ago, a paper from 1967 by the authors names of Robert Mishell and Richard Dutton. It's published in the Journal of Experimental Medicine, and it is entitled Immunization of Dissociated Spleen Cell Cultures from Normal Mice. And this rocked the world and really established cellular immunology for the immunologists, some of them anyway, because of the fact that it talked about antibodies. It's the same old thing. If it wasn't anything to do with antibodies, it wasn't really immunology. So this is really a methods paper in the Journal of Experimental Medicine, and it's quite long. It has 13, 14 tables, couple of figures, and a lot of methods and a lot of results, essentially, all published in these tables, which was sort of the way things were still going, even into the 60s. But it's really the first, what I realized in reviewing all these papers and so forth, it's really the first sort of modern style paper in immunology. The other ones were either just, presentations of data and interpretations of experiments without any materials and methods, as I've said before. And so this was really the first one to go into the nitty-gritty, the details, so that other people could hopefully reproduce what these people were talking about. And just in terms of a little bit of the background, Bob Mishell was a postdoc. He was an MD, actually. He was a postdoc with Dick Dutton, who was a PhD, and they were at the Scripps Research Institute in La Jolla. And so they were Californians, they're a little bit different breed than the rest of us. Dick Dutton was an interesting guy. He was a Brit, grew up and was educated in Cambridge, both for his undergrad years and as well as his graduate years. And I haven't looked into why he jumped ship and came to the New World, but he did, and he spent his entire career in the United States. He had a little bit of a touch of a British accent. And Bob Mishell was sort of a little bit of a wild man, He really he marched to his own drum. They set to see if they could do something that nobody had ever done before. And this paper from 1967 rests on a paper from 1963 that I glossed over and I didn't talk about earlier. But if you want to read it, it's on the website. And it's by Niels Yearning and Al Norden from 1963, 3 rather than 7. So this is 4 years later. And this paper is only one page and was published in Science. And it describes, really for the first time, the first experimental proof that McFarland-Burnett's clonal selection theory was actually true. So this was the beginning of establishing the clonal selection theory as a law in immunology, because what they showed was they could show by using techniques that I'll tell you about in a second, that single lymphocytes would secrete antibodies in the surrounding medium and lyse red blood cells that were being used as the antigen. And the way they did this was quite ingenious, although it took on from a lot of things that had developed over the last 50 years in serology and antibody activity. What they did was they took rabbit lymphocytes from lymph node or spleen or whatever else, and sheep red blood cells. So it's 3 different species: rabbit lymphocytes, sheep red blood cells, and guinea pig serum as a source of complement. And what they did was that they took the sheep red blood cells and they mixed them with agar and put them in petri dishes on the ground layer, on the bottom layer, and at a quite a high density, so that the whole petri dish took on a red hue from the sheep red blood cells. And then on top of that, they mixed rabbit lymphocytes in agar, heated it up to like 40, 45 degrees so that it was liquid, poured it over the sheep red blood cells. But because the lymphocytes were in agar as well, they couldn't move. They were stationary and they were fixed right there. Then on top of that, they added the guinea pig sera as a source of complement. And of course, complement is together with the right kind of antibody will poke holes in cell membranes and in this instance, the red blood cells, they would lyse the red blood cells. And so what you could see under with the naked eye, but even better under a low power microscope, an individual lymphocyte and then a halo all around it of lysed red blood cells. And so it was what they called it was a plaque. And of course, in the days of microbiology, which everybody had grown up from, lytic plaques and so forth were quite commonly, and this whole business with the petri dishes and the agar and everything else had been used in microbiology over the course of the last half century. Anyway, that only took one page for them in Science to describe. And actually, that's one of the things that Niels Yearning, who was this Danish physicist who left physics and decided to get into biology and then subsequently immunology. I think physics was too hard for him, so he jumped camp and he went into immunology. It's one of these classic papers that Yearning went on to win the Nobel Prize in immunology, and I think it was 1984. So it shows to go, you don't have to write long papers, just little ones, as long as they're very, very smart. Prior to this paper that was published in '67 in the Journal of Experimental Medicine, Mishell and Dutton had really published the phenomenon that what they did was they combined Yearning's assay for antibody forming cells, which would be AFCs, which would cause plaque formation, which they called plaque forming cells. What they did was that Mishell and Dutton published a shorter description of this '67 paper in Science that came out in 1966. And essentially what they did was the Yearning paper, you had to have immunized the rabbit in vivo first with sheep red blood cells. And then if you wait a while, then you took the lymph node or spleen cells out, you could do these experiments and get these plaques. And you could enumerate them. One of the most important things was that you could quantify how many plaque forming or antibody forming cells there actually were. Now that's important. And as I think I told you a long time ago or a while back, Sir Peter Medawar said that you can accomplish a lot in science simply by quantifying things that other people have described. And so this is what Yearning's plaque assay did. But if you took rabbit lymph node cells from an unimmunized rabbit, you didn't get any plaques. So there was still a black box associated with this whole phenomenon. And what Mishell and Dutton wanted to do is to take the whole lymphoid system out of the black box, which is what they did. And this is what we'll describe in this paper. And in the introduction of the paper, they basically state in the very first sentence of the paper that this report describes in vitro and in vitro system for the study of the factors. We'll get back to those factors again, like those lymphodrek or lymphokines, that control and regulate the cellular events of the immune response. And so this is cellular immunology par excellence. And this paper went on to become probably one of the most well-quoted papers in the history of immunology. The other thing that they said say in this paper is that they compared what they were able to do was to generate an in vitro primary immune response, so that they didn't have to immunize the rabbit or the mouse or whatever beforehand. They could just take cells from a normal lymphocytes from a normal animal, put them into culture, and then add antigen. In this instance, they used the sheep red blood cells, and then they could do the Yearning plaque assay. So they could do the whole immune response, primary immune response in vitro. That was big. That's why I got into Science in '66, and that's why this methods paper became a classic in immunology. So in the materials and methods, they describe their whole system. And they first talk about the fact that they would put these cells into culture media, and they had to have serum in the medium, which was really standard in tissue culture at that time. Remember, tissue culture really only started in the 50s, and so it hadn't been into the mainstream for very long. Everybody knew that you just couldn't use the tissue culture medium, which is really a balanced salt solution and so forth. You had to have a source of serum. And by experimentation and so forth, people had come to the conclusion that fetal calf serum was better than adult cow serum, probably because the adult cows had enough immunological experience so that they had antibodies to just about everything in the environment. And so they would muck up your experiments. Whereas the fetus, the embryo, the growing embryo, hadn't gotten sullied by all these environmental antigens. And so, you ask yourself the question, where do you get fetal calf serum? Well, you get them from fetuses. And so in the slaughterhouses, they were sort of indiscriminate about whether the cow happened to be pregnant or not. It got slaughtered, and then they took the fetuses, and then they found out that there was this market for the fetal blood and serum, and so they harvested that and they sold it on the side. You you do what you have to do. Anyway, for the biological people that were into culturing things, fetal calf serum became the standard fare. But as I'll get into, these particular kinds of experiments, you had to have the quote unquote best fetal calf serum. So you had to get fetal calf serum from many different biological supply houses. And then you had to test each batch in your experimental system to find out which would give you the best results, the greatest results, essentially. That becomes important as time goes on, and as I'll talk about. Then, in order to get a source of complement, they had to take fresh guinea pig serum. So you had to have guinea pigs around the lab, and you get these guinea pigs. You could freeze it away, but it had to be fresh. You couldn't let it sit around. So that the complement, which were a source of the molecules that would poke the holes into the red blood cells and lyse them, so that that was your indicator method. That had to be fresh, the guinea pig serum. They used Eagle's minimum essential medium, which essentially, as I said, Eagle was an investigator in Philadelphia in the early days of tissue culture. He devised his own recipe for tissue culture media. So he used Eagle's MEM, and then you would add 5% fetal calf serum, and then you'd supplement that medium with essential amino acids as well as non-essential amino acids. And that became the critical media that would make this whole reaction happen. Then you had to have the cells at a very high density. There was a thing at this particular point in time where the dogma was that it's the same old story as if you had a Swiss clock and you take it apart and lay out the gears and all of the internal workings on the desk. Clock doesn't tick anymore, And so it was thought to be the same thing in immunology. If you took the cells out of the architecture of the spleen or the lymph nodes and minced them all up and created a single cell suspension, then it wouldn't work. And this paper basically says that's not true. It will work, but you got to use a high cell density, 20 million cells per milliliter. That was important. It's usually 10x what most people use to culture lymphocytes. And they would take that 1 ml and stick it in a 35 millimeter Petri dish, which is about this big around, 1.5 inches of diameter. And then you'd add red blood cells to that, sheep red blood cells, or you could use other species of red blood cells. And they looked at different concentrations of the red blood cells and found that 3 million red blood cells per ml was optimal. And then you would put these Petri dishes, they had plastic boxes constructed, they were about the size of a shoebox with plexiglass, and you could look into you could see what was going on in there and so forth. And then not only, they thought, well, instead of fixing the cells, they wanted the cells to bump into each other and so that they could get activated by the antigen, the sheep red blood cells. So they put them on a rocker panel that would rock back and forth 7 cycles per minute, very, very gently like that. This whole thing went into the incubator and then was gassed at a special gas concentration. Room air has 20% oxygen and 80% nitrogen and very small amount of CO2, and then other things, but very trace. So here what they did is they reduced the oxygen concentration, and they usually use 7%, but they found that they could use 7 up to 20% oxygen and it would be okay. If they surpassed 20% oxygen, then it was toxic and everything would die. hyperoxia. And they used 10% CO2 in the gas mixture. And that was basically designed to mix with sodium bicarbonate in the tissue culture medium, the Eagle's MEM, to maintain the pH at a physiologic range, or at least start off at about 7.2 to 7.4. Then, and the rest was nitrogen. And then not only that, they had to then come in to the lab every day, even on the weekends, and feed those cultures. And they had a special cocktail of nutrients that was basically the medium with the amino acids supplemented, as well as their special batch of fetal calf serum, a little bit of that. And so they take a little bit of medium out and they put this nutrient business into them. Then when they did the plaque assay at the end of, so that they would culture this would rock back and forth for several days. And then they could take aliquots out every day or whenever they wanted to, and they could do the yearning plaque assay with the sheep red blood cells and then in the agar and so forth. So that was how they did these experiments. And of course they worked all these things out. They did a lot of fundamental experiments to try to optimize each aspect of all this business. You can imagine it took them a while, I'm sure. That's Bob Mishell probably drove himself crazy doing all these experiments. So in the results section of this paper, they found the following, and there's a whole list of things that I'll talk about here. First is the standard cultures. They found that if they before they started the cultures, if they looked at time 0 and did a yearning plaque assay, it was 0. There were no plaques when they started out. Then if they took out aliquots every day for several days, they found that like day 4 or day 5, they would get an optimal response, having added the sheep cells at time 0. And that optimal response with the plaque assay was 1,000 plaque forming cells per million spleen cells, mouse spleen cells. It's all in the mouse now. So that's only 1 out of 1,000. Not a whole lot of reactivity, but they weren't surprised about that because this is a primary immune response. There aren't supposed to be too many antigen reactive cells in an unimmunized animal that's naive and has never seen any sheep before. So they did a series of experiments and they reported 20, and they said all in series, said all 20 experiments were successful. And that was important. There wasn't any variability in this whole business. There was one problem that they noticed. If they set up control cultures without any sheep blood cells, red blood cells at time 0, and then assayed for the plaque assay at day 4, 5, there was some background plaque forming cell response of about 100, a tenth of what you could do if you put the sheep red blood cells in there. They didn't know why that was, and they speculated in the paper that it must be, they surmised that was because there was something in the fetal calf serum that must have been antigenic, some cross-reactive antigens with sheep red blood cell antigens. And so if you set up the cultures just with the mouse spleen cells and no sheep red blood cells, no antigen, you still got sheep red blood cell specific plaques on day 4, a tenth of what you got if you added the sheep red blood cells. So that's a little crazy. And that turns out that's very, very important in retrospect. And one of the things that I have found as an aside in rereading these papers again and again and again is how much things change over time. So 50 years later, we know an awful lot of stuff now that those guys did not know back in 1967. The other thing was if they put 2 times 10 of this 20 million cells into the culture at time 0, by day 4, they lost cells and they only had like 35 to 40% cell recovery from what they started with. So that tells you that what was going on during this time period was a deterioration of the viability of these cultures. That's not such a good deal. That could be a problem, essentially. The other thing that they did, though, that was very, very interesting is that they assayed the culture supernatant from these cultures at day 4 and 5, and they could look for antibody in solution that would hemolyze sheep red blood cells, and they found it in the supernatant of these cultures, which was good, but only in those cultures that had been activated in vitro with the sheep red blood cells. If they didn't put those in, they didn't get any antibody out the other end. But that was good for them. They figured, well, that's consistent with us making a primary immune response. And the antibody they measured was a IgM, which is characteristic for the primary immune response. And so everything fit, and they were very pleased with that. And that was very good. And then they went in and they reported, and each one of these things that they examined ended up in a table, and that's why there are 13, 14 tables in this paper. They looked at the gas. They found out that 7 to 20% O2 was the right way to go. They did different cycles. And they found out that 7 cycles of the rocking platform was best. They found out the optimal spleen cell concentration of very high density cells at 20 million cells per ml, the red blood cell dose. They tested a whole bunch of other species, burro and horse, and other sources of red blood cells that they could get their hands on, and they all would work. They could immunize against all these other species of red blood cells. And finally, they did experiments where they took immunized mouse sera that had antibodies, and they stuck it in the cultures at time 0. Antibodies to sheep red blood cells, and they stuck it in at time 0, and it blocked the reaction. That was also good for them because they said, okay, well, this is a real immunological experiment. That's what we're looking at. And then finally, they compared their so-called primary in vitro immune response with a secondary immune response, with using spleen cells from mice that had previously been immunized in vivo, intravenous inoculation of sheep red blood cells. They'd wait 4 or 5 days, and then they'd take the spleen cells from those animals. And that turns out that was very important in terms of how everything worked out in this whole. They compared the various batches of fetal calf serum that they were using for their sheep red blood cells versus normal mouse serum. And herein is, to me, I think, the most important aspect of this whole paper. Only when they used cells from mice that had been primed in vivo could they get a plaque-forming cell response with normal mouse serum in vitro. If they did that whole thing with normal and unprimed mouse spleen cells with mouse serum, there was no plaque-forming cell response. Whereas if they used fetal calf serum, they got it. And so the fetal calf serum was really important for the so-called primary immune response in vitro, which is what they were purporting to show in this particular paper. Now, the other critical thing is that when they looked at the secondary immune response from the primed sheep red cell primed mice in normal mouse serum, the secondary immune response in normal mouse serum was sky high. It wasn't just 1,000 plaque-forming cells. It was like 70,000. That was an average over 4 or 5 different experiments. But a primary wouldn't work with using the normal mouse serum. So what's going on here? And to make a long story very short in terms of this whole thing, what's going on there is that fetal calf serum in the slaughterhouse, as they're taking the serum and the blood from these poor fetuses that they're sacrificing, would get contaminated with bacteria. And the bacterial cell wall, as you know, is in a lot of bacteria is comprised of endotoxin or lipopolysaccharide, LPS. And what was not known at the time was that LPS is a mitogen, non-specific, non-antigen specific mitogen for mouse B cells. Doesn't work on human B cells, but it causes mouse B cells to undergo a proliferative response and then to secrete IgM. We know that now, and we'll probably get into those papers in about 10 or 15 or 20 years from 1967, where they pinned that down. But I think all of the things that they saw in this paper, in terms of what they thought they were seeing as a primary immune response, is really a response to the LPS, the lipopolysaccharide in the fetal calf serum. And if they had stuck to their mouse serum, they wouldn't have been deluded that they could do that. And it really relates to the frequency of antigen reactive cells that get activated. And as I said, in the unprimed animal, it should be really very, very low, like 1 out of a million. I don't even know the frequency of that. So that you shouldn't have been able to generate and detect within just a few days a primary immune response. And that's one of the other reasons is that's why we do we're now into the COVID era. That's why we have 2 doses of a vaccine. Because with the first dose, you expand the number of cells, they proliferate, they expand, and so forth. And so now, rather than 1 out of a million, you got 1 out of 100,000 or 1 out of 10,000 or even 1 out of 1,000. And so when you get your second dose of your COVID vaccine, now you've got this is what a primed host really is. You got many, many more cells that are going to be reactive to that particular antigen. And so these experiments with sheep red blood cells 50 years ago are really the forerunners of all the things in immunology, that the kinds of things that we're trying to do today to stop this crazy pandemic really rest on. The other thing is, the other reason that this paper became so well cited is that if there was another paper that they published at the same time in the Journal of Experimental Medicine that followed on immediately thereafter. And in the second paper, they showed that in order to get an antibody, the plaque-forming cells had to arise by having at least 1 round of DNA replication and cellular division. And they did this with what they called a hot pulse technique of very high specific activity, radioactivity, tritiated thymidine, and that would kill off any dividing cells. And so the data are very convincing. So you might want to read that paper too. It's not on the website, but you can find it out of the library if your library gets the Journal of Experimental Medicine. So the other thing they showed in this paper is that if they put 2 different red blood cells in there, say burro red blood cells and sheep red blood cells, the different populations, there were different antigen-specific cell populations that were responding to those sorts of things. So that's it. And I think that it's interesting because the cellular immunology crowd that arose after this paper was published, they were basically in 2 different camps. There were the camps that wanted to measure plaque-forming cells because they were interested in antibodies. And then they were the so-called cellular immunologists. Those were the humoral immunologists, the ones interested in antibodies. Whereas the cellular immunologists ultimately became the T-cell people. And the 2, so that we had 2 opposing groups. It was sort of like the Democrats and the Republicans, and as to whose philosophy was most important in this whole process. Listen, if you really like this whole journal club or like this particular video, go online, like the video, click on the little bell so that you get notified every time we do this. We usually put these videos out on Monday morning. So with your coffee and toast and so forth at 8 o'clock, you can access this and get entertained by Kendall. Also go on the website and check out the writing tab from the homepage, because then if you scroll way down, you'll find all the papers of the classics of immunology, and it's really a repertoire of all of immunological science. And if you persist in this journal club, whether you're a scientist or not, you're going to learn immunology backwards and forwards. You're going to understand these commentators on television.